morning. I'm Jack Dongera and chairing this session. I'd like to welcome you to this plenary invited speaker session. Our first speaker is Matthias. He's a principal researcher in the quantum group at Microsoft. After receiving his PhD in 1994 from the ETH Zurich, he spent time as a postdoc at the University of Tokyo before returning to Zurich. There, he was a professor in computational physics until taking a leave of absence to join Microsoft's quantum computing program at the beginning of 2017. He is a fellow of the American Physics Society, a recipient of the Raman Prize in Computational Physics of the American Physical Society. His research interests span from high-performance computing and library design for scientific computation to the simulation of quantum devices. At Microsoft, he is now working on various aspects of quantum hardware to quantum software architectures, new applications for quantum computing, and customer engagements. The title of his talk is A Quantum Future for Computation. Matthias.
People ask me why I work in quantum computing, and the answer is very simple. When I had to choose my master's thesis project, there was one topic where I could use a Cray YMP supercomputer, and so that was the topic I chose. It just turned out to be quantum. But what I really want to do is use the best and fastest machines to do new things, and for me that is now quantum computers. And before I start, I want to give the word to some of your colleagues what their vision is. So I want you to see not only the vision, but to see through the hype and learn what's realistic. And you'll see that what's mentioned here will be the future. But there's also lots of hype out there that I want to debunk. The basic idea is that new physics always leads to new technologies. Thermodynamics led to the steam engine, electromagnetism to electronics. Quantum technology is new. But what it can do is it can make us finally change the way we compute. Because deep down, the way we work on the fastest machine now is the same as the abacus. The principles of how we compute have not changed in thousands of years. With quantum computing, we can change it. And the basic idea is that quantum computing, as was mentioned, just is different. Let me illustrate this. When we think of light, we usually think of it as a wave. But we also know that light is a particle when we send single light particles, photons, through a fiber. So light can be both a wave and a particle. With matter, we think of electrons circling a nucleus. They are particles. But in 1924, de Broglie asked the question, is matter really only a particle, or should one view matter also as a wave? He proposed that in his thesis in 24, and 5 years later, he got the Nobel Prize. And this is basically the principle that we use. We can view matter also as a wave, the wave of an electron around the nucleus. And now let's take those principles of quantum physics that we've known for nearly 100 years and apply them to a computer. Let's look at a bit. If the electron is in the left box, it's 0. If it's in the right box, it's 1. But now let us view that same electron as a wave. And the wave is not just in one, but it's in both boxes at the same time. So it can be both 0 and 1. It can be more 0, more 1. There can be phases. But that's the basic idea. Let's view the basic bit as a wave, as a quantum bit. Of course, if you take that to the extreme, then you get to Schrödinger's cat. A cat that at the same time is dead and alive. We haven't seen that yet. That doesn't mean it doesn't exist. It just shows us how hard it is to make something big be in many states at once. And if that sounds weird, then I want to give the word to Richard Feynman, who invented the quantum computer, and let him talk about quantum mechanics.
In a time when only one did, because he's the only guy that caught on before he wrote the paper. But after people read it, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, I'm going to tell you what nature behaves like. If you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing.
So if Feynman even, who co-invented quantum mechanics, admits that he doesn't really understand why it works that way and says we should just accept it, then maybe that's what we should do. And so the idea that we have is we want to use it now. We want to accept that nature is weird, and we want to use it to build a quantum computer. And our goal is to build a system that is scalable, that can really scale to millions of quantum bits to solve big problems. We don't just want to build some demo. We want to build a real system to solve problems that are just unsolvable on any imaginable classical computer. So it's not just post-exascales, it's post anything we could build classically. And to do that, we have to work on the full stack. We have to work from the quantum bits, the foundation to the cryogenic systems, to cool it down, to the classical control of the quantum system, the error correction, the software stack, the algorithms, software applications, up to the cloud integration into Azure. And this is one of the few projects that I know where I can work on the full stack from the hardware to the applications. And that makes it exciting. It also makes it hard. To show the challenge, just if we want to scale to 1 million quantum bits, we have to feed 1 million lines into such the cryostat. We can't do that. It would heat things up. So what we'll have to do is we have to control it all from the cold stage. We have to cool all of the control logic to 4 Kelvin. We need completely new classical logic to even control it. But we also need, as the foundation, that quantum bit that can be both 0 and 1. And there are many quantum bits out there. Yeah, you can build them from ions that move around and vibrate or not. That could be T0, 1. It could be the currents flowing in a superconductor. It could be the magnetic moment of an electron. All those work as quantum bits, but they're noisy. You cannot do more than about 100 or at most 1,000 operations before they lose their quantum nature. They're extremely susceptible to noise and don't live long. Building things from that is kind of like trying to build something exascale from vacuum tubes. We didn't do that, and we wouldn't even dare to do that because they burn out too fast. Before going to exascale, we needed to invent the transistor and then the integrated circuit. And same here, we need to first get better quantum bits. And we need to make sure they are not susceptible to errors. We need quantum error correction. But in principle, that can be done in software. It leads to a huge computer. It's much better to start with better hardware. And so the basic idea goes back to the Incas. The standard qubits we have can be compared to just chalk marks on a board, but any local noise when it rains or something will destroy it. The Incas encoded information in knots in a string, and that's much more robust. Because you can take the string, move it around, shake it, and so on. The knots in the string will not be changed by that. And we want to do the same with quantum bits. The idea goes back to Ettore Majorana, who invented a particle called what's now called the Majorana particle. And soon after that, he boarded a ship to Sicily and vanished from the face of the Earth. We don't know where he went or what happened to him, but we found the particle. We can make it in devices. Then as we move those particles around, we can basically make knots in the history of these particles, and that encodes the information. If that sounds weird, think of Feynman. Except that nature can be that weird. But now, how do we actually want to make that quantum bit? Yes, we still encode it basically in electrons. If there's one there, it's a 1. If there's no electron there, it's a 0. But that's something that's extremely susceptible to noise. I can't just look if it's there. But now what one can do is one can take this electron and split it up into 2 of those Majorana particles. So we basically take an electron and split it into 2 pieces. And those 2 pieces have no features. If I look at them, I don't see anything. But when I bring them back together, then I see either that those 2 particles form an electron, or they form no electron. They either form the bit 0 or the bit 1. When they are separate, I don't know it. So encoded in something non-local, that no local noise can ever find out what the state is, and no local noise can ever destroy the state. That we can build in a hybrid superconductor semiconductor devices. We have those already. We could see the particles. We're working now on getting the operations to work. We're getting there. It's a tough project, but it's basically totally new physics, which is exciting here. And based on that, we have a chance of really building good quantum bits that are scalable. Let me switch now to what we do when we have it. I said that quantum bit is like a wave. It can be in the left box or the right box. It has an amplitude alpha 0 to be in the left box and amplitude alpha 1 to be in the right box. And so the state of that one quantum bit can basically be described by 2 numbers, the amplitude of the wave in the left box or the right box, the amplitude of 0 and 1. Together, it has to be normalized, so the alpha 0 squared plus alpha for 1 squared must be 1. That shows you already that to encode the state of a single quantum bit, I need two complex numbers. And so one could naively think I can now store basically infinite information in that. But we can't, because when I read out the state of the quantum bit, then the same thing happens to your Schrödinger cat at home. When you look at the cat is either dead or alive. When I look at the quantum bit, I measure it, and I either get a 0 or a 1. When I look at where a particle sits, it sits either in the left box or the right box. It's no longer a wave. As long as I don't look and I compute, it can be in both boxes. When I look, when I read it out, it turns into a classical bit. So I get a classical bit with the probability that is proportional to those amplitudes. If the wave was more in the left box, then it's more likely to get the 0. If it was more in the right box, it's more likely to get a 1. So that shows you already I need two complex numbers to describe the state, but I get only one bit out when I measure it. Let's go to more quantum bits. Let's go to n bits. For n quantum bits, there are 2 to the n different bit patterns. And so I can describe it by 2 to the n amplitudes. So I need 2 to the n complex numbers to describe the contents of n quantum bits. So when I have 30 quantum bits, I need about 16 gigabyte. 40 quantum bits, I would need about 16 terabyte. 50 quantum bits, I would need about 16 petabyte. We may get such a machine, hopefully soon. But let's say we go to 100 quantum bits. We can't build such a machine. And if you want to go to 260 quantum bits and want to store the state of those 260 quantum bits, you would need more classical bits than there are atoms or even subatomic particles in the entire visible universe. And that's what I mean when I say we will get to problems that I just cannot represent with any classical computer. Now, this just says I cannot describe that state on a classical computer. I cannot simulate it, but how would I use it for something interesting? First, it can solve problems that I cannot solve classically. For example, the RSA-2048 challenge. Here's an integer. The task is finding the 2 prime factors. The estimate is that to do that on a classical computers with algorithms we know on the fastest machine we have would take about 1 billion years. If we get a quantum computer with about 4,000 qubits, I can do it in 100 seconds. That's the type of problem that we want to solve. Of course, no, I don't mean cryptography. Of course, we joke that when we have about 2,330 qubits, we could use it to steal all the bitcoins in the world, and that might fund our program, but that's a one-off application. That's not interesting. But it shows that quantum computing will impact us all. For cryptography, what it means, we need to switch to quantum hardened cryptography, which could either be using the quantum hardware or using crypto systems that are not susceptible to quantum attacks, and that's what we work on in that space. But it's more interesting to actually solve real computational problems that we can't tackle on any HPC system without quantum. And naively, people often say quantum computers are exponentially faster than classical ones because they can operate on all values simultaneously. The quantum register can be in all possible values at once, so it can operate on all values at once. This is a myth I want to debunk. It's only a partial truth. Yes, it's right. I can view it that I take my quantum register, I put in a single state like 0. Then I can prepare a quantum superposition of all possible values. This would be like having an exponentially large SIMD register with exponentially many values in it. Then I can compute on all those values simultaneously. Great. And then I read it out. And remember what I said, what happens when I read out a quantum register? If it's an n-bit register, I get only n bits out. I pick a random value from my big register. So I can view it as exponentially many values, but when I read it out, I randomly get one of the answers. And that doesn't help me anything, because I could just as well have just started with a single input. So the trick and the hard thing in quantum computing is when I have this big exponential quantum superposition, to turn it into something useful, to do a useful quantum reduction that gives me just a few almost deterministic classical bits back. And this part is the hard one. And this is where the key lies in designing quantum algorithms. And we don't have too many reduction operations. To show what we have, I use a slide from Thorsten Höfler, because this is an HPC conference. I want to mention my colleague at the ETH. He made a nice slide showing basically the 5 different building blocks. There's Grover's algorithm that can amplify a certain state. There's a Fourier transform. That's the basis of the factoring algorithm. There's phase estimation. There's something to give you eigenvalues and the eigenvectors. There are quantum walks that speed up the mixing time or the time of your probabilistic algorithms, and you can simulate nature like quantum physics and chemistry. These are the 5 building blocks. So a quantum computer will never replace our classical HPC systems. It will be an accelerators. While quantum computers are Turing complete, they can in principle do any operation that a classical computer can do. They are also much more expensive and much slower for that. Their strength is not in doing classical operations. Their strength are doing specific tasks where we have a quantum algorithm that is exponentially faster than any classical one. So they will be special purpose accelerators. Thinking about programming them is also different, because these quantum bits are extremely hard to make. The quantum bits will be super expensive. We'll be happy when we have 100 good ones. But operations on them are cheap. Just keeping a quantum bit alive is as hard as manipulating it. Basically, operations don't cost. Just keeping the memory alive is what costs. That makes you think of how can you do things with less memory. Then there is the potential for exponential speed up, but I have overhead. The machine is slower. Computation is reversible. That gives us overhead. I cannot copy quantum information. Control flow is hard because I'm in a superposition of all possible states, so any control flow has to be turned into predication. And then there's the readout problem. These are the challenges we face when we program the quantum computer. So now the question is, after you've seen all the hype at the start, what will you then actually do once we have that machine? When I talk to people, they tell me many different answers, from better drugs to curing cancer, fighting hunger, solving global warming, and much more. When I then think about that, it looks to me like this is a list for a quantum wishing well. There's a huge set of problems where I just know I want to solve them. I don't know how. Maybe quantum computing can help me because it's so powerful. And what I work on nowadays is trying to think about for which of these problems can quantum help and how. And we found some. So to develop a quantum application, we have to look at one of those problems and find a way how can we solve it better on a quantum computer than on a classical one. So we want to start out by finding a quantum algorithm that has quantum speedup, meaning the time to solution scales much better than on any classical computer. For example, exponentially better in some cases. That's what most quantum information theorists did. They proved theorems that the asymptotic scaling is better. For me, that's only the starting point. Because once I have that, I want to confirm that the quantum speedup really remains after I implement my whole program, including I/O. Then I have to optimize the code until the runtime is short enough. Because I don't care when it's exponentially fast asymptotically if it runs for 1 billion years. The program should finish in a few months. And then in the end, I have to embed it into hardware and find out what machine I need. What we need for that is a new breed of quantum software engineers. They're hard to find because what we need are people who know quantum computing, who know quantum mechanics, but who also know classical HPC. They have to know how the problems are solved classically. They have to know the competition, the classical one, to then find the problems that you can solve better on the quantum side. So we need people who know quantum and HPC. Let's start from one problem, optimization. In any local search algorithm, I might be stuck in some local minimum that I need to escape, and there could be a really tall barrier. Not in Texas here, where it's flat, but in the mountains, in Switzerland, for example, we have high mountains, and it's hard to escape a valley. Now, any classical algorithm has to classically climb over the barrier, separating that from the global optimum. But on a quantum computer, the quantum particle can quantum tunnel through the walls. And when the barrier is tall but narrow, then it's just much easier to tunnel through it than to climb over it. And so with quantum tunneling, one can sometimes get exponential speedup compared to classical optimization. And that has been implemented in the quantum annealer by D-Wave. They built a system with quantum bits. They built something analog to solve a very specific problem, namely to solve a quadratic binary optimization problem with quantum effects. This problem is NP-hard. So if one finds a fast way to solve it, that has big implications. The good news is such a quantum annealer, which is analog, can be built with imperfect noisy qubits. They've scaled it to more than 2,000 qubits, and that was a big achievement. Really, controlling 2,000 quantum bits, well, that's a challenge. That's the good news. Less good is that I saw that, I said, I must use that. It's much better than the YMP. So we tried it, and unfortunately, we did not find any advantage over a classical computer. And over the years of studying it, we realized that this great idea of quantum tunneling can be simulated classically. That's great news. It's great news because it tells us that we can mimic quantum tunneling on classical computers. We can do it now. We can do quantum optimization now with 0 qubits on standard classical HPC hardware. And just thinking about quantum algorithms gave us new ideas that we can implement now on classical computers. It gives us new algorithms just by thinking with a quantum mindset. And we found here that I showed the time to solution for the problem class. In black, the quantum annealer. In red, the much better scaling of our quantum-inspired classical algorithm. We can even get classical speedup over a quantum optimizer. Some people think that's bad for quantum computer. I think it's great news that we can have impact now. One example is the automaker tried to solve a traffic optimization problem. They solved it on the quantum annealer 40 times faster than on their supercomputer, namely 20 seconds. My student could then solve the same problem with our quantum-inspired algorithm in 200 milliseconds. And we can do it another 300 times faster using FPGAs in Azure. So a problem that somebody used to run for 20 minutes, we can now solve in milliseconds time. That problem might be too easy. We use it now to optimize pulse sequences for magnetic resonance imaging in the project checked with the Case Western Reserve University. And that's where we hope to have an impact by making MRI faster and more accurate at the same time. What that gave us is one example of dequantizing quantum algorithms. We can do things with quantum-inspired methods now. And in the future, those algorithms can be further accelerated on quantum hardware. But we already have value now. But you didn't come here to hear me talk about classical algorithms coming from a quantum mindset. So let me go back to true quantum algorithms and find something where it's really useful. And one provable example is database search using Grover's algorithm. And here I quote from a European Union document that says that quantum computers will really accelerate database search. Because if you have an unsorted database, Grover's algorithm can find an entry in square root of n queries if you have n entries. What this ignores is that any one of those square root of n queries has to load the whole database. Not even a quantum computer can look through a database without you loading the database first into the quantum computer. I/O is a serious problem. In the classical world, it's even more though quantumly because it's slower. And whenever you have to load data, and you can solve the problem classically in a time that is proportional to the data size, a quantum computer cannot give an advantage. So Grover search is a great root solver. It solves an equation. When you can compute your database, then it's fine. When it's real data, it's not a solution. So I like to say that big compute problems are better for quantum than big data problems. It's not a machine for big data, it's a machine for big compute problems. And so let's look at a big problem that not even Summit can solve. We look at chemistry problems. A small molecule, no problem that can be done classically. We go to a large one like the FEMOCA molecule, and no classical computer knows how to solve that. Understanding that molecule would be super interesting because this is the molecule at the core of the protein that some microbes use to make fertilizer from air very cheaply. If we could understand how that works, we could get a new way of making fertilizer, but no classical computer can simulate that molecule accurately enough. However, nature can do it, it just works. In those microbes, the molecule just works, and it works because nature uses quantum. Nature is quantum mechanically. Nature uses quantum physics to operate, and so it can use it. And Feynman's idea in '81 then was to say, hey, if simulating physics or chemistry on computers is hard, because I have to store these exponentially many complex numbers that describe this quantum state of nature, then the answer is simple. Let's just use nature to simulate nature. Let's just use the quantum aspects of nature to build a computer that uses quantum physics to solve those hard problems. And that's where the idea of a quantum computer came from. Let's just use quantum physics in the computer to solve those quantum problems. And thus, you can solve it exponentially faster than on any classical computer. For example, a simple molecule, redoxin Fe2S2 is a benchmark case that is intractable on any existing classical computer, but which is exponentially faster, provably so, on a quantum computer. And then we implemented the algorithms. We optimized the algorithm. We assumed a fast quantum computer, and we estimated the runtime for one simulation. And we found it's about 3,000 years. For kind of a benchmark molecule, that's just at the threshold of where it becomes hard classically. We would like to do much bigger ones. The problem behind this is, yes, this has been proven that there exists a polynomial time algorithm. It just scales with the 11th power of the number of electrons. If somebody gives me an n to the 11 algorithm, then I run out of the hall. So what we have to do is we have to optimize it. And in this case, we could bring the runtime down to an estimate of about 3 hours once we have fast good qubits. What that shows is you don't just want to prove that there is a polynomial scaling algorithm, you also have to optimize the algorithm. You have to do more than just proving things. You have to write fast code. So that's then the third step in getting to quantum applications. You have to optimize the code until the runtime is short enough to be feasible. I don't think 3,000 years to be, but I can wait days. I call that quantum HPC. Because we don't just want it to run, we want it to be hyper-performant. And the tricks we use to get the runtimes down all have the analogs in classical HPC. We looked at the code and we tried to optimize it as much as possible. We reused computations where we could. We reordered the terms to enable better parallelization. That gave us the factor n, each of those. We optimized the code for the local kernels. That gave us a factor 4. Then we reordered the terms to get the time step errors down. That gave us a factor 10. The most importantly, I think we can get much more here, is when you look at a molecule, then you have some forces that are large and many forces that are tiny, tiny, tiny. And so when we propagate this in time, then we have to use small time steps for the large forces. But the tiny force terms, we don't have to do every time step. We can do those tiny terms every 10th time step or every 100 time step with just the 100 times bigger time step. So using large time steps for the small terms and small time steps for the large terms gave us a big advantage here of at least a factor 10, maybe a factor 1,000 or more, and so on. So most of these are tricks we also do in classical HPC. We have to apply the same knowledge to quantum algorithms to get codes to be fast. We do that with the Microsoft quantum development kit that you can download from our webpage. We have a new programming language, Q#. We thought at first doing it just as a library. It turned out to express the constructs you need for quantum. It is much better to define your own language. It is integrated into Visual the Studio. There's syntax highlighting, documentation. There are debuggers. We also ship it with the simulator. The local one can do up to about 30 qubits, and on HPC systems went up to 45 qubits. And by doing the simulation, we can actually inspect the state. It's much better to debug a quantum algorithm on a simulator than debug it on real hardware. Because in the simulator, I can look at the state. On the quantum hardware, that's much harder. And then we have lots of libraries, samples, documentation. It runs on Windows, Mac OS, Linux, and so on. What we realized when starting to implement quantum algorithms is that essentially all of the non-trivial published quantum algorithms implementations are buggy. They didn't work. You implement it exactly as in the paper, and it doesn't work. Why does it not work? Yeah, because nobody ever tested it. They just wrote it in the paper, and it is super important to actually implement it, and that's what we did. Then we find out it doesn't work, then we debug it, and we find if you think debugging on a petascale system is hard, debugging a quantum algorithm is even harder. We fixed things, and sometimes it was easy. Just one gate was missing somewhere. Sometimes we realized that there's a fundamental flaw in the algorithm. So it's super important to start implementing them now, testing them, and so on. We applied it then to problems like nitrogen fixation. How do we make fertilizer? Currently, we use the Posh process, which uses 3% of the world's natural gas production. There is this microbe I mentioned that can do it at room temperature, ambient pressure. That's the molecule here. With 200 quantum bits, we can solve that problem. So what we did now is we said quantum chemistry is one of the first killer apps. We partnered with the Pacific Northwest labs to make a chemistry library that plugs into NWChem and will in the future accelerate chemistry simulations on quantum hardware. You can now already test it and find out how many qubits you need for your problem. To wrap up, there's more that I did not talk about. There's quantum machine learning. If you have a machine that you cannot simulate classically, then that's a great opportunity to maybe train it to learn data much better than any classical machine can do. That's a big open question. Can the quantum entanglement, the quantum superposition help us make machine learning models that are much more accurate than any classical model? That has to be explored. There's also more. There is quantum money. And I think the big market might be in quantum games and quantum social networks. If all teenagers in the world want to have their quantum bits in quantum superposition with their friends' quantum bits, then there may be a market much bigger than HPC. So we may not know the real applications yet. The take-home message is quantum computers are getting closer. They will be accelerators and not replace classical computers. They will be useful for small data, big compute problems. But already today, by dequantizing quantum algorithms, we make progress on classical hardware. And there's lots we can do in the future. when we have big quantum computers. Thank you.
Okay, I guess we have no questions. Thank you so much for your presentation. It was really great.
Thank you.